Our participant is a young man, is married and has a small child. His biggest wish was to be able to communicate, talk to his son as he was growing up. ALS is it's short for amyotrophic lateral sclerosis, also known as Lou Gehrig's disease in the US. And it's a progressive neurodegenerative disease. It's pretty rare, and it affects neurons in your brain and in the spinal cord, the so-called motor neurons. People affected by this disease progressively lose all ability to move. They lose the ability to breathe on their own, end up often in a completely locked-in state.
People who have become completely locked in have no means of communicating with the outside world. They can't move muscles, they can't move their eyes, and they are really in need of a solution like a brain-computer interface for communication.
Participation in this study means undergoing brain surgery, having these small electrodes placed into the area of the brain that's responsible for movement. The signals travel down from the electrodes through the wire to this connector, which is attached to the skull. On the outside, we have an amplifier that digitizes the signal and sends the signal, the activity, to a computer. So what we really want to pick up is the activity from the brain as the person attempts to perform a movement. And whenever the person, for example, tries to move the eye, we see change in activity. So cells suddenly start to spike, fire, and we can pick up this activity. We convert these spikes into what we call firing rates. And then we listen all over the array to all these different cells, combine the activity from all these cells. Whenever the person is attempting to move, he can't move, but attempting to move, we see these changes, and this is our signal for communication. This person cannot see clearly, which is just a consequence of the disease. So we're using auditory feedback. We assign a yes to the high-pitched tone and no to the low-pitched tone.
Ja. Nein.
And then we can start to ask questions. We can ask the participant yes and no questions. Do you feel well today? And we wait for a response. A high-pitched tone means yes, he's okay. A low-pitched tone means no, does not feel well today. We can go even further. We can use these decisions to control the speller. Now we're using the very same principle of groups of letters being presented one after the other, and the participant, through his brain activity, selecting or not selecting groups of letters and individual letters.
Ja. Nein.
For example, he asked his son if he would watch Robin Hood, the movie, with him.
Aktuelle Satz bist. Nicht wo sie willst du mit mir bald bis nach oben hoch anschauen anhalten.
At the B Center, we developed the NeuroKey software to flexibly process neural signals. And for us scientists, this is really important because we don't necessarily know right from the start what we have to do with the brain signals to be able to decode messages from our participant.
When we were starting to build this brain-computer interface application, we looked at the software that there was available in the market, and there was no software that filled the gap of what we needed for this particular study. So what NeuroKey is bringing to the BCI community is the medical-grade certified software that it's also optimized to work with implantable devices, that is capable of processing lots amounts of data in real time, coming from hundreds of electrodes and tens of kilohertz of sampling frequency. And also NeuroKey gives the possibility of easily prototyping and building your BCI application.
We've shown with the system that we developed that even people in completely locked-in state who have no other way of communication can communicate with their brain signals.
The thing that is really important, and that's something that both Louise and my team are working on, is to have a system that's fully implanted and works at home. That's the only way to get it reliable enough for a person to be able to use it in daily life.
So at the V-Center, we're working on a fully implantable device that will be completely hidden. This is experimental technology. Our mission is to further develop this technology and improve the lives of people with paralysis.